Am I audible to you? Manish, am I audible to you?
Yes, sir, you are audible.
Start the session. So, in case of the electromagnetic field theory and transfer line, this course actually where we have 6 modules. Out of that, 4 modules covers the electromagnetic field theory, and 2 modules covers the transfer line theory. And so, before going to the transfer line theory, we have the last module that is on the electromagnetic theory, that is the module 4, which describes the electromagnetic wave propagation in different mediums and how this can be described in mathematical form, which is very fundamental for the many of the important concepts, particularly the wave propagation. So this, for instance, whenever we transmit a signal, let's say we have a transmitter and this is going to transmit the signal in a particular direction, and this will be received by another antenna, and we have received. And this wave propagation, how this takes place and how we can understand this behavior. By understanding this, we can make this antenna system as well as this transmitter receiver signal, which are operating in a particular frequency. So everything can be understood very clearly. And not only this, this particular wave, when it propagates through different mediums like dielectric medium or conducting conductors, how this will behave. So in order to understand this, we are having this mathematical formulations. We will see some interesting applications in the upcoming classes. So for today, we are going to describe the wave, how this wave behaves, and in mathematical form, we are going to describe. So let's go into that. Yeah, this works whatever we are seeing in terms of the wave propagation or in general electromagnetic waves. The concept of this started with Maxwell. He was challenged by his own idol, that is Faraday itself. So Faraday was almost dying, like 2 years before his death. Faraday met Maxwell. Maxwell was around some 22, and by that time itself, he has solved many important critical problems, and both are from same country. So that is one reason. Otherwise, if by this time, if Faraday would be there, he would have called the other person to come by flight. So, but Maxwell himself is a genius at that time. So he called and they started to talk about the very fundamental problem that he has to prove that this the light is a electromagnetic wave. So Faraday told that for me it is convincingly true, but it's supposed to be done with mathematical work. And so this is one of the important reason he started to describe the wave behavior of the electromagnetic field. So this is actually one of the very important crucial point. In fact, that is true. In one of the important work, you will see that the phase velocity of the phase velocity of the wave will come 1 by root of epsilon naught mu naught will come, so which is simply nothing but the velocity of light itself. So this clearly tells that the electromagnetic wave, so the light is the electromagnetic wave itself. So we can see some more interesting concepts over the period. And yeah, we have already discussed about this Maxwell's equations in various forms, and we will recall them again today. So let's go to the topic, the wave propagation. So before that, we have to discuss what is this wave itself. So wave is uh, a disturbance or a oscillation, anything you can call, or a change in a particular quantity. This quantity can be energy, this can be electric field, magnetic field, power, or potential, or current, So you can call that by any means, and so that is going to be a uh, function. Actually, that is going to mainly that is going to transfer the energy in some other form. In case of the sound wave or the water wave or whatever it is, they are also carrying energy only. So the energy is manifested in different forms, and one of the manifestation itself the wave. And so this can travel with matter or without matter also. So that is another important properties of the wave. And so most probably this wave will not disturb the existing medium, or it can move the medium up and down, but it won't cause the lateral changes, which means that if there is a water wave and if there is a ship, and it won't disturb the ship, it will go up and down alone. So that is what we can say in that way. So these are the typical understandings in the wave itself. All, of course, you also be understood about this. But this wave, we are actually having two important types. One is actually longitudinal wave. So in this, the energy will be traveling in the along with the direction of the wave itself. If the wave is traveling in a particular direction, when it go on hits, then the energy will be transferred in that particular direction. But on the other hand, we are having another type of wave that is called transverse wave. In this, the wave propagation will be in the perpendicular to the direction of the if the wave is traveling in the z direction, it may be in the x or y direction, it may be available. So, and it will carry the energy also in the same direction. So when you square that particular field component, you will easily get the power term or power term, and you integrate the power term, you will get the energy. By that, you can easily understand that. So in this case, the very important question should be asked that should they require any medium to convey this or to describe this the oscillations or the the movement of the particular energy system, which is electric or magnetic field or water, whatever it is. So in case of the longitudinal waves, which generally often referred as mechanical waves, so they actually carry the energy in the forward direction along with the direction of the wave itself. So they tend to have or require medium. But in case of transfer waves, the energy is perpendicular and it is not going to depends on any medium's behavior. So therefore, there is no medium is required for them. So they can simply travel along that. And one of the important example is electric and magnetic fields. Also, this is same applicable to light also. So this is why from the sun, earth, there is no nothing else. There is completely space vacuum is available, but still the light wave actually traveling along that. And some people still they are actually describing that like it there should be some fundamental nature which describe the space, and that is going to be the medium for the light wave to travel. And so that is what people sometimes recently believing as bosons. So this boson, uh, which actually described by Higgs, but before Higgs itself, um, S. N. Bose already described this behavior, and this is actually he told that you just to take any particular atom and you just to put it in the temperature very close to that of 0 degree Celsius. Then this atom, which look like a particle, this will behave like a wave. And so this is completely true. And so in fact this is the very same situation which could be describing the Big Bang and all the way. However, later Higgs added his descriptions about this in the mathematical form, and I think Higgs got Nobel Prize for this as well. Also, one more work that if this atom is put into less temperature, it will become wavy behavior. This also described as Bose-Einstein condensate. Those who proved this temperature, this at the low temperatures, which is very hard experiments. In fact, people used to say that it's the coldest place in the universe like that. So it is. So they also got Nobel Prize for this. So such a very wonderful work. And in fact, by digging up this same wave propagation towards this boson, if you're successful, you can define the matter in terms of the wave behavior itself. Maybe you will get Nobel Prize for that. Not only this light wave, gravitational wave also kind of a longitudinal, sorry, this transfer wave. It can travel over the space without any medium requirement. So this also detected in, I think in 2018, they detected when two black holes collide each other. It created kind of a space wave, which we call gravitational wave. This wave, when it reaches the Earth, it is creating this kind of signature. So this is actually recorded by a project called LIGO, and so this is one of the very important experimental work. And this matches with the behavior, which in fact even 1.3 billion years light years before this event happened, but still it could be recorded, and it matches with the theoretical simulations. So it is believed that the light means the gravitational wave exists, and many concepts could be summarized in this. So this wave, there are different types of waves are available. One of the most important one is the plane wave. The plane wave describes that all the wavefront of the wave will be having same phase velocity, which means that if this is the origin of the wave, you are dropping this some stone, or you are actually exciting this, or some radiation, some antenna is there, it is radiating some amount of power, as then it travels, and this at any particular point, if you take the wavefront, this wavefront will be having the same phase velocity. In other words, all of them will be available in same time, and thereby you can here anywhere else you just to take the measurement, they will be giving same phase only. So the phase of the wave will be same, or at any particular instantaneous time, you will get the same properties for the wavefront. So that is what we refer as plane wave. So in this plane wave, whenever you take with respect to time, we will get constant behavior. That is why we always take this d by dt or dou by dou t is a constant, like that we will take. So that is applicable to wave, plane wave. There are other types of waves like cylindrical waves and spherical waves. For instance, the water wave is a kind of a cylindrical wave, and here also we can expect very similar behavior. But this will all the things will be explained in terms of the cylindrical, and spherical waves are still further uh, will go in a straight line, and you will see that after this splits, you can see that it is going in the circular manner. And so this kind of waves are called spherical waves. So this is the general property. So a wave can be converted into another form by means of some disturbance. For instance, you just take a metallic tube. In this metallic tube, a wave is traveling, and immediately when you decrease the size of that, then this all the wave, to maintain its equilibrium, they will tend to move. So in this case, the wave which is traveling in this direction, it may travel in the other direction also. So that kind of manipulations also could be possible. So, and in case of electromagnetic field theory, many important works are described in the plane wave condition itself. In many cases, it is also true. And maybe after the reflection only, some kind of disturbance will happen. But still then, the plane wave is worth to study. And the plane wave can be described mathematically, that whenever there is a wave exists on a particular medium, okay, we have some space, and in that particular space, if there is a wave is traveling along the particular medium, then if and the medium is isotropic means the wave will be uniform throughout all the directions. That means the radiation intensity or the field intensity E or H will be same throughout the direction. and it is having source free. Source free actually means this medium don't have any charges. Therefore, the charge density will be zero. Let's say charge rho v equal to zero. And of course, there is no current or there is no any current is available. So therefore, the J also will be equal to zero. So by this, there is no charges or no current, and the medium is homogeneous. Of course, throughout the space, you will be having same uniform medium is available. And so this in this particular case, naturally the plane wave will exist because the plane wave is supposed to have all the wavefronts of uniform phase velocity. If this is not true, then the such a behavior cannot be exist. So that this is the very fundamental requirement for a plane wave. So the plane wave naturally exists in isotropic and source free and as well as homogeneous medium. So in order to derive the mathematical expression for the plane wave, we are taking Maxwell's equation. And so in this in this four Maxwell's equations, you can find there are two equations already having this time dependent behaviors, and two are describing about this electric and magnetostatics. So in this, we are going to apply this four conditions. Isotropic and homogeneous applies that this the mu and this epsilon, which are nothing but permeability and permittivity, both are constant throughout the space. Therefore, we can say that this dou by dou t of B can be written as, which is where we know that B is nothing but mu h. So where mu can be taken out, which means with respect to time, this mu is constant. So you can take it as mu h dou by dou t. The same thing we can do for D also. And we are going to apply source free. Source free tells that the current is zero and charge density is zero. So you will get this particular term is zero and the charge density will become zero. And this this will become mu dou by dou t of h. And this particular term will come epsilon dou e by dou t, like that will come. So in this three, therefore this four equations are converted into this type. And so this is the Maxwell's equations, which are describing the electric and magnetic field in this particular medium. That means such a medium can exist. Now, in order to derive that, we are going to take a curl of this first two equations. So the equation number this and this, we are actually going to take the curl of that. So curl of electric field, curl of magnetic field. So if you apply that, you will get this equation. So both the side, when we do the curl, so for this magnetic field also, we will get the curl. For this electric field also, we will get the curl. So we have done on both sides. And this operator is a and we already know that this dou h by dou t is nothing but epsilon dou e by dou t. And similarly, del E by del H is this. So we are going to substitute this 2 in the other equation. So you can see here, this is actually substituted by this expression, and this is substituted by this expression. And by this way, we will get this electric field in terms of electric field, and the magnetic field will come in terms of magnetic field. So this is one reason simply tells that electric and magnetic field, they are nothing but manifestation of each other. And we can take this mathematical identity of the del operator, and by this way we can easily get this expression. So we are going to take this two equations as a left hand side, and these two equations are nothing but right hand side. So we are going to substitute, and we should note that this del dot H and del dot E will be equal to 0. Therefore, you will get del dot H and del dot E will become 0. So only these two terms will exist. So you will get minus del square E minus del square H, which are equal to minus mu epsilon dou by dou T of, we can simply take the square of that, dou by dou T square of electric field. And here you will get minus mu epsilon dou square by dou T square of H will come. You can cancel out this negative term, then you will get this equation. This is actually this originally derived by Maxwell, then later rephrased by 2-3 people, and one of them is Heaviside, and another one is Helmholtz. So these are some genius mathematicians. They have described much more clear aspects of the this electromagnetic field theory. In fact, both the books actually written by the name electromagnetic field theory. Both genius, they have written independently by themselves, and so these equations celebrated later. Helmholtz equations later went towards the antenna theory, and Heaviside equations derived with respect to transmission line theory. So we will see that Heaviside's works in the next module. So in this equation, we are going to rearrange and we will get this equation. So this is famously celebrated as the vector form of the plane wave, and which is often referred as the Helmholtz equation. So most convincingly, people will used to write that this is called wave equation. So very similar wave equation. This is actually for electromagnetic waves. Similar wave equations are available for mechanical systems as well, like water wave, and for music, which are created from the strings of guitar. All these things we can find. So those were actually described by people like Bernoulli and Euler. So we got this wave equation. Now, if you solve this wave equation, then we can see that this electric and magnetic field, how they are related, and what is their nature with respect to time and space. We can easily see that. And that is nothing but wave equation, or the solutions of the wave equations. So so now we are actually going to do, we are going to take that, since we are considering the plane wave, this dou square by dou T supposed to be constant, because already dou by dou T is already constant, which we already discussed here. And for considering the plane wave, in that case, this is going to be the constant. So in order to describe this as a constant, we are introducing a new quantity called wave number, the angular frequency. So the same later can be defined with the phase velocity as well. So this is called angular velocity, and minus dou square, therefore, this is equal to minus dou square by dou T in order to make this term as a positive one. So by the way, you will get these two equations, and at any particular time, you will always, at any particular time as well as space, or throughout the space, we will get dou square by dou T is nothing but minus omega square. And this is only applicable to plane wave. Now, this is the these are the two equations we are supposed to solve. So how to solve? It is very simple. We have this, so we are bringing these two terms in the right hand side. We got this equation. Now we have famous, like this at del square. So you will get two solutions. One is in the positive side, another in the negative side. So that is what described here. We have the forward side, or along the, because this you can understand that this del square is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is nothing but del square operator. So for each and every direction, we will be having two different solutions, or cumulatively we'll having two different solutions, and these solutions will be along the space. So in the space, we have two directions. One is x in the positive direction, x in the negative direction. Like that, we have two. Now, if you assume that the wave is actually traveling along the z direction, then these two naturally will not exist. Only this alone will exist. So we are going to take the wave propagation along the z direction. By this, we will get along the plus z direction, along the minus z direction, you will get two waves. So here you can see that the first term is describing about the wave traveling in the forward direction, which is often referred with E plus, and which comes with this e power j omega t, which actually derived out of this. And we have e power j beta z, where this beta is nothing but the the phase constant. And similarly, we have second solution, that is nothing but the traveling in the negative direction. You will see that the forward direction will be defined with minus sign, and the reverse will be defined with plus sign. You need not to confuse that. And in fact, we can also exchange that. There is no problem, but this is a standard way people used to define this. So we got this for electric field. Same solution will be available for the magnetic field as well. So we got electric and magnetic fields available. And since both are perpendicular to each other, if the electric field is available in x-axis, this will be available in y-axis. And if x is available in y-axis, then the z will be available in minus x-axis. Like that, it will be available. So, which clearly indicate that in a plane wave, the wave can be existed in a particular medium, which is source free, homogeneous, as well as isotropic medium. There are two possible way the wave can exist. One is traveling in the forward direction and traveling in the reverse direction. It is possible, and it is having two components. One is the electric field in the perpendicular direction, and perpendicular to the magnetic electric field, we have another, that is the magnetic field will be available. So this you can see in many places. You will see this picture. The electric field will go in this way, and the magnetic field will go in this way. So this is actually Ex, and this is Hy. Along the z-axis, the wave is traveling, and the electric and magnetic field, they will be continuous each other. They will exchange the energy by themselves and travel over the space. So this is these two are the solutions of the wave equation, and they are nothing but waves. And in this, we can take only one particular wave, which is actually traveling in the forward direction, and that too we are going to take only the electric field. So the electric field available oscillating in the x direction, and it is traveling in the z direction with respect to the time. So that is described this, and you can see that this is going to be describing the time behavior. This is going to be the space behavior. So here it is traveling in the z direction with the constant velocity of constant phase velocity. It is traveling, and it is a exponential. It is the description of in terms of exponential form, and if we convert that into cos and sine in real and imaginary, you will see this. So this is the real part. This is the imaginary part, which comes with the imaginary operator. So we got this too, and the magnitude is available here. And in this, we can see here the wave is actually traveling in the z axis, which is often comes with minus beta z, and it is having a constant phase velocity. So here, whenever this beta changes, the wave velocity will change, and obviously the wave whichever is available and its behavior, everything will change. And considering this phase that is omega, we are going to assume always it is a constant one, because we have assumed the plane wave. So this is what the wave wave equations, which gives the behavior of the electromagnetic wave, how it can exist. Okay, so it is like a condition. So in this, any one could be possible, either as a real or imaginary. Both cannot exist together. Any one will be available. So how to understand this? Assume that in the in a particular free space, you have there is no charge density, there is no conductivity, there is no current. Okay, so completely it is a empty space. In this, you have put an antenna. Okay, so you have put some antenna. This antenna is going to excite the wave, and it is connected with the time varying signal. So this current will go, and this current will generate electric and magnetic field, and that is going to propagate. And depends on the way it is placed and the way it is excited. It may exist as a sine, or it may exist as a cosine waveform. In any way it is possible, but either of the one only could be possible, not both. That is why both are orthogonal to each other in terms of real and imaginary part. Okay, so now we have seen that how the wave can exist in a particular medium, and how now we have to describe the wave itself. So this is the general form of describing the wave. We have the quantity which is oscillating. Here it is electric field. We can have magnetic field. We can have power. We can have current, voltage. Many things could be described. And it is traveling along the z direction, and it is varying with respect to time as well. And it is having a magnitude, and the solution, which is nothing but sine form. We can also have cos form, and the omega is nothing but the angular velocity or angular frequency, and the time operator, and the phase operator, and the propagation, the phase constant is available. And this description often refers the phasor representation, and it is a time harmonic signal, which means that with respect to time, it always will give the constant oscillations, and which we can't expect with respect to the space direction. So that we have to keep in mind. And so that is how we are describing the wave propagation. And that is why it is called time harmonics. And since it is a time harmonics with a constant frequency, obviously we can have multiples of its frequency, and we will get frequency harmonics also could be possible with the same. And A is the amplitude, and this term, this omega t minus beta z, is called as phase. And so this describes that how fast it is, how the time dependent signal is traveling along the space. And of course, omega is referred as angular frequency, and the beta is referred as phase constant. And in some other physics books, you can find this as a wave number. And all these quantities are described in terms of the wavelength and the time period and everything else. So the wave, this is how the wave is traveling along the z direction. And so we already described about this radius, this angular frequency, and the wavelength. The wavelength, we know that the distance between the two successive maximas or minimas. So that is nothing but the wavelength. So with respect to this wavelength, this wave is going to repeat. And this is actually introduced by this term, the phase velocity. And this phase velocity will become velocity of light for true electromagnetic waves, which are available in free space itself. And so this can be calculated by 1 by root of mu epsilon. And so whenever the dielectric and magnetic permeability of a material is changing, then its phase velocity also will change. And in this, when you substitute this mu r equal to epsilon r equal to 1, then you will get the same phase velocity will become 1 by root of epsilon naught mu naught, because mu is nothing but mu naught mu r, and epsilon is epsilon naught epsilon r. So you will get this term remaining. When you substitute these two quantities, you will get velocity of light. You should remember that these two are nothing but the constant which are derived out of electrostatics, but they are actually exist in the dynamics also. That is, in the time dependent wave fields also, this is exists. So it is going to be the universal constant. Therefore, the velocity of light is constant everywhere. And this is one of the very important understanding one has to take. And this can be calculated by this omega divided by beta. Otherwise, lambda f also can be calculating this phase velocity. And beta is nothing but the wave number or the phase constant. So this can be calculated by 2 pi by lambda. And by describing this lambda, we can easily substitute in terms of phase velocity and the other quantities. So this phase number is directly proportional to the dielectric material properties itself. So the wave will go fast or late depends on the dielectric material. So for instance, the phase velocity is inversely proportional. So if we take, say, one is silicon dioxide and another one is titanium oxide. So the wave whichever is traveling, and in case of titanium oxide, it will go slow because here we have this epsilon r is 100, while this value epsilon r is approximately 4 only. The T, of course, time period, everyone knows about that. So when this wave is actually propagating along that, we can specify in terms of the space, but this position always be described in terms of time. So this time of oscillation is having connection in both cases. So which is already described with this one as a phase velocity. And the wave can travel along the forward direction, that is z, along the reverse direction, that is minus z, and this will be called as forward traveling wave. And this is actually reverse traveling wave. The wave will travel always in the same direction. And when both wave meet each other, let's say you have forward traveling wave, reverse traveling wave at uh, the same omega t, at the same beta z, then we will get an interesting factor that they will cancel each other or add each other. So you will get wave behavior like this will come, and this is we call standing wave. This doesn't look like traveling. The wave will always look like a standing wave with respect to each other. Okay, now, so far now we have discussed about the wave that exists in a isotropic homogeneous source free. But this is not always true. For instance, if you consider the air medium, there are some types of charges might be available. In that case, the wave behavior will completely change. And that is described with the conductivity of the medium. If the conductivity is not equal to 0, then there exists some charges. If there is an existence of charges, then we can't substitute this. We can't say that this del uh, del dot d is equal to 0. If del dot d is not equal to 0, that means the wave which is traveling along the space at every particular point, we can't expect the same magnitude. Due to this charge or charge conductivity, this amplitude will keep on decrease. So that is what we can expect in a uh, a medium with charges. And since the magnitude is decreasing, the medium will be often referred as the uh, lossy medium. So whenever there is the existence of whenever there is the conductivity is not equal to 0, such a medium will be referred as the homogeneous, and in fact isotropic, and it as well as the lossy medium. So for such a lossy medium, we will always get this conductivity also along with the other phasor terms. So far now we have the phasor term as this J omega epsilon mu, and along with that we will add the conductivity as a real term. Then you will get this wave equations. So, and in this the real and imaginary part of this material property will be described by this gamma square, where this gamma square, because these all terms will come in terms of squares. These all terms will come in terms of squares. Sorry, up to here. We should remember, because here it is square, here also it is, you will get dou square by dou t. I believe you have still remember that. That is what we have converted to omega square. So we will always define that as a gamma square, which is this particular factor. And so this is often referred as propagation constant. So this propagation constant describes how this wave behaves, how the wave propagates, and that is described by J omega, and the term, the real part is going to define how far this amplitude is going to be affected. In general, amplitude is going to keep on decrease, means in an exponential manner over the distance. So that is described by this, the real part. So this is often referred as the phase constant, and this is going to be described the attenuation constant, which means that assume that there is a medium. This medium has conductivity is not equal to 0. That means there are some charges exist, and this charge is going to make the field discontinuous. And this discontinuous is, which can be described like this. We have an antenna. This antenna is going to create an electric field along the, and it is going to travel along the z direction. And along the way, it will keep on decrease its amplitude, which is very well true. We could see that the electric field is keep on, the magnitude of the field is keep on decreasing. That is why from the tower, when the signal reaches, the amplitude is reduced, and we are sometimes saying that the means the not reachable like that. So this is a very true phenomenon, and that is described by this attenuation. So it is the attenuation or the phase. It is not the properties of the wave. It is properties of the medium itself. That is manifested in terms of the wave behavior. So that is what it is described. Alpha is the attenuation constant. Beta is the phase constant. Together they are named as propagation constant. So here the real and imaginary part brings together a simple equation like this. Yeah. And I'm sorry, in between, yeah, by this way we can easily say that this del square, let's say in terms of magnetic field, which can be defined as gamma h gamma square, we can say gamma square hs. So now we are going to take the solutions for that, and you will get two solutions. One is along the positive side and negative side, like that you will get two solutions. And further we can define this, we can take the real part of that gamma, and you will see that, let us take this equation and take the square of that. You will get alpha square plus beta square, and which is nothing but the real part of this itself, and you will get this equation by stating this equal to alpha and this equal to beta, like that you will get this equation. And when you take the magnitude of that, you will get alpha square plus beta square. So that also we can easily calculate. Now when you add this equation, let's say this is equation number A and this is equation number B. When you add this equation, you can easily get the alpha square. When you subtract these two equations, you will get beta square. From this you can calculate the value of alpha and beta in terms of omega, epsilon, mu, and the conductivity sigma. Within this three scope, you can, within this four material property, we can define this attenuation and the phase constants. So that is what it is calculated here. So this is the standard form of attenuation constant and the phase constant of a particular medium where the wave exists. And in some other physics books, you can find this two expression which described with the epsilon dash and epsilon double dash, where epsilon dash describing the permittivity, where this epsilon double dash is going to describe the loss of the particular medium. Anyhow, we will always use the standard expressions only throughout our course. And by this, the plane wave which is described in this way can be reduced to like this when the wave is traveling along the z direction. So we have to solve this equation, and the solution, you will get two solutions. One is along the positive side and negative side. Similarly, for magnetic field also, you have positive side and negative side. And you got this expression. And when you divide the magnitudes of them, say we are having positive and negative is equal to E naught, and positive and negative is equal to H naught. When you divide them, you will see that both are related by a new quantity called the impedance. So we very well know about the Ohm's law, that V equal to IR. So where this voltage describes the electric field and the current describes the magnetic field, and this R is going to describe the impedance. In these kind of we use this eta as the variable to describe the impedance in the space. Anyway, this also takes the same value. Ohm itself will come for this. So when you divide these two equation, then you will get this eta, and this eta is you will get root of this j omega mu divided by sigma plus j omega epsilon. Okay, when this medium is lossless medium, when there is no charges available, the medium will become lossless. We will get charge density is equal to 0. When the charge density is equal to 0, then this term will be cancelled, and you will see that this omega term and this term will cancel each other. You will get simply eta is nothing but root of mu by epsilon will come. And such a medium will be having only so-called the magnitude part alone. There is no phase term, which means that the wave will not create any phase lead or phase lag between the two waves, electric field and magnetic field. There won't be any phase change. That is what we have seen here, that both the waves will be in phase. So whenever you draw the electric field will be drawn this, the magnetic field will be drawn this way. So both are actually in phase. But whenever there is a phase change, you will see that the electric field will go like this, and the magnetic field will start from little later, and it will go in the other space. And so this is what described with magnitude and the phase form. And we can easily calculate the magnitude and phase. Both we can calculate using these two expressions, which are calculated out of this expression only. And this loss 2 theta will be often referred as loss tangent. So here we can see in a lossy medium how the wave will exist, how the wave look like. So the electric field will exist along the direction of z, and it will vary with respect to time, and where it will be having a magnitude with the alpha, and the wave will propagate with respect to omega. So this alpha, you can see that it is exponentially decaying function. So from the starting point, when it is traveling over the space, the amplitude will keep on decrease. This is the general properties of the wave. On the other hand, this magnetic field is nothing but the electric field divided by the wave impedance. But the wave impedance has its own magnitude and the phase term. and this phase term will be added along this 2, and the impedance will directly affect the magnitude, and the phase will affect the phase term itself. So you will get a new quantity for the magnitude of the magnetic field along with this attenuation, and there is a change in the phase term. So there will be a shift due to this phase term with respect to the space itself. So this is what we can see, and this phase can exist from 0 to 45. Within that only it can exist. After that, by rotation, we have to subtract by another 45 degree. So this is how the two wave will exist, and this is the example when this theta is equal to 0. You can see that the wave is traveling, and the magnetic field also exactly perpendicular direction it is traveling. Both the zeros are meeting at the same point. But rather, if the theta means theta eta is not equal to 0, then you will see that there will be a shift in this two waves. And this attenuation, the attenuation constant, always described with another important quantity called loss tangent. And so this is describing that whenever the wave is traveling, it has the conduction current Jc as well as displacement current Jd. So as it is keep on traveling, this Jc can be converted into this Jd. So in other words, the wave, whenever it is traveling in a particular medium, due to this loss of energy due to this Jd, we will get losses. So to describe the losses, we always define this conduction current divided by displacement current. When you substitute both the expressions, you will get this quantity. This quantity already we have seen here in the phase of the medium itself. So the phase of the impedance is this, so which is described as a new quantity called loss tangent, where loss tangent can be calculated from the medium's impedance with the 2 eta. So once you have described this four properties, omega, sigma, and mu, epsilon for a particular medium, then you can clearly write how the impedance of the particular medium as well as what type of wave can exist and how this wave will keep on decay. Everything we can easily calculate. Let us take a simple example and finish this work. So assume that there is a lossy medium and it has this the moment we say lossy medium, that means sigma is not equal to 0. This we have to keep in mind. So, and then the impedance naturally will exist for it. So the impedance is written here. So the magnitude of the eta is there, and the phase is also there, which is nothing but 200, and this is going to be 30 degree. And this frequency is not mentioned here, and the wave, it is propagating, the plane wave is propagating on this dielectric, which has the magnetic component. So we have two components, one is electric and magnetic. In this, the magnetic field is described here. So our job is to calculate the magnetic electric field and the attenuation constant alpha. So here we don't have any knowledge about this epsilon and the mu, sigma, and omega. This 4 data is not at all available, but still we can easily find these all things. So for this, first we are going to calculate the electric field. Okay, first we have to look at this magnetic field. The magnetic field is oscillating in the y direction. That means along this z direction, if this is actually x direction, the magnetic field is available. If magnetic field is oscillating in this so-called y direction. Okay, and the wave is actually traveling along the x direction. So this is the x direction then this is supposed to be the z direction. Now the question is, in what direction this electric field will be available? So very simple, that if you use the right hand rule, then if you rotate the magnetic field in the clockwise direction, you will find the corresponding minus z direction. This, so you will get the electric field will be available just in this direction, minus z. So this can be calculated by taking this ay cross ax. You will get minus az vector itself will come. So that is what the direction of the electric field. So this is, so we found the direction of the electric field, and now we can easily calculate the magnetic field. So we already know that the eta naught and divided by h naught is going to be eta. Therefore, E naught is nothing but eta h naught. We already know h naught value, which is this, and eta we know, which is nothing but 200 into this. So, which already described. We have this value, we have this value. So it's just we are going to replace all of that, and with this minus ay vector. So az vector is coming, and corresponding minus term is coming here, and this E naught value is placed here. Cos term, there is no change in the cos term. Omega and this beta also, there is beta x also, there is no change, where we can easily say that beta x equal to x by 2. Therefore, beta is 1 by 2. And this is the extra phase term added. So this is the description of the electric field. Now we can calculate this alpha by simply applying this two equations. So we have alpha and beta value we know that. So how to do that? We are going to take the ratio of this alpha divided by beta. Many terms will be cancelled, like this term and all will be cancelled. We will be getting this sum of some terms alone, and we have substituted here. And in this we know that sigma by omega epsilon is nothing but 2 tan 2 eta, which we already have seen in the description of the impedance itself. And we already know this value, this theta is nothing but pi by 6, which is nothing but 30 degree. So when you substitute here, you will get tan 60 degree, which will be nothing but root 3. And when you substitute this root 3 here, then you will easily get alpha by beta will come. And we already know beta value. Beta is nothing but 1 by 2. Therefore, alpha can be calculated. Alpha is calculated here, and the unit is Newton per meter. So this is how we can easily calculate. And furthermore, we can even calculate other quantities like sigma, mu, epsilon. We can easily calculate. And we will take one more example in the next class. So this is what the wave propagation happening in different mediums, in the lossless medium and versus in the lossy medium. So I believe you got that. I have taken the class a little more longer. I'm sorry for that. So